Only press release today is from Melina, right?
It's the only one I have, yes.
Okay.
There should be one from me coming at some point, but it was all very last minute.
Okay.
Okay, Shantanu, we're ready to go.
Okay. Hello, everyone, and welcome to the Tuesday, October 27th press conference at this virtual DPS. My name is Shantanu Naidu. I'm the DPS press officer. And with us today is also Rick Fienberg, the AAS press officer. He'll help us with the Q&A and other technical issues that may arise. Just a reminder, if you missed yesterday's press briefings or if you want to revisit them, they're available on the meeting website. If you click on press information and go to the second media advisory, under the schedule, you can find links for their presentations, the YouTube video, and press releases, if any. We'll be recording today's press briefing and also streaming it live on YouTube at the AAS Press channel, where it will also be archived for future viewing. So this is how things will proceed today. I'll give you brief introductions for the speakers, the panelists, and their topics. All the panelists will speak in order, and then we'll go to Q&A. If you have any questions for the speakers, please type them in the Q&A feature, and be sure to indicate your affiliation and the presenter towards which your question is directed. You can also upvote on other people's questions to raise them in queue. And we've asked our presenters not to answer questions via text while other presentations are ongoing, but we will answer them live during Q&A session so that they appear on the YouTube video. Okay, with that, let me introduce the speakers. First off, we'll have Melina Rice from Yale University, who will be talking about surveying the Trans-Neptunian solar system with TESS. Next, we'll have Buratti from Jet Propulsion Lab, Caltech, who will talk about Pluto in glory, discovery of a huge opposition surge. After that, we'll have Rohini Giles from Southwest Research Institute. She'll be talking about the Juno UVS observations of transient luminous events in Jupiter's upper atmosphere. And finally, we'll have Noemi Pinilla-Alonso from Florida Space Institute at University of Central Florida, who will talk about the irregular limb of Manoetius South Pole and improved orbital solution. Okay, so I'll hand it over to Melina to start her presentation. Thank you.
Thank you, Shantanu. Just going to get this started. All right. So hi, everyone. My name is Melina Rice, and I'm an NSF Graduate Research Fellow in the Yale Astronomy Department. And today I'm excited to share with you results from a new survey of the Trans-Neptunian solar system, that is the region beyond Neptune with the Transiting Exoplanet Survey Satellite, also known as TESS. The project that I'm presenting today is specifically focused on Planet 9 and related objects, and the associated paper has been accepted to the Planetary Science Journal and will appear on the archive tonight. So our image of the solar system is a relatively tidy one that looks like this, where all the planets lie neatly in approximately the same orbital plane, implying that they formed in the same disk of circumstellar material. So we have this nice and simple picture, but there's a lot more to this picture that's been slowly unraveled over time. So this picture is only showing the inner 30 AU of the solar system, where the known planets lie. Solar system bodies have been discovered far beyond the Neptune of orbit, or far beyond the orbit of Neptune. These are known as extreme Trans-Neptunian objects, but this population is not well understood and its constituents show a few unusual properties. They tend to lie on orbits with a relatively high inclination and eccentricity relative to the solar system planets, and beyond that, they show an unexpected apsidal and nodal alignment. That is, their orbits are clustered roughly in the same plane and roughly in the same direction in the sky. These have led to the proposition of a potential ninth planet in the solar system, popularly known as Planet 9, that could help to produce these observed properties. Now, zooming our solar system way out to show the distances to scale, if Planet 9 exists, and that's a big if because it's never been observed, it would be located at a distance of 400 to 800 AU. It would have a mass of 5 to 10 Earth masses. That's the size of super Earths in exoplanet nomenclature. It would be inclined at 15 to 25 degrees relative to the solar system planets, and it would be on a fairly eccentric orbit. This helps to explain why Planet 9 may not have yet been found if it exists. It's incredibly distant and therefore very dim despite its large size. So how can we search for such a planet or other objects at these vast distances that have not yet been explored? The TESS dataset is remarkably well suited for just this purpose. TESS was designed to search for undiscovered exoplanets around bright nearby stars, and it's phenomenal at what it does. So far, it's identified thousands of exciting new exoplanet candidates. But TESS also provides a goldmine of data that can be used to study much more than exoplanets alone. Over the course of its survey, TESS observed nearly the entire sky outside the plane of the solar system. That's the gap you'll see in between the northern and southern surveys in this video. And TESS stays at each pointing for around 27 days. So we have nearly a month of photons continuously collected in each region of the sky. We effectively get 2 missions for the price of one. A mission to study exoplanets and another that is ideally positioned to search for Planet 9. To recover the signals of extremely dim objects, we need to collect the month's worth of photons all in one place. We accomplish this using a method called shift stacking. If an object moves across the frame like this, that's equivalent to changing your frame of reference such that the object stays in one location and you slide the image past instead. This illustrates how our new survey works. We take a month of data from TESS, pre-processed to remove stars and systematics from the light curves, and stack our pixels along an orbital path. Here we're showing real TESS data and an actual recovery of Sedna, an extreme Trans-Neptunian object around 300 times dimmer than Pluto. This video is another way to visualize that process. The left panel shows our reduced TESS frames over time in the vicinity of Sedna after we've subtracted the baseline flux of each pixel. So what remains is mostly foreground asteroids passing through. The right panel then shows the sequential sum of the images on the left, shifted and stacked along Sedna's path. So on the right, we begin with an empty region in the frame that gets filled in over time as the frames are shifted and stacked leftward. We see the signal of Sedna pop up nicely in the upper central region of the right panel. And it's pretty likely that this video might be skipping frames in your view because of the limited bandwidth of Zoom. So I encourage you to go to the link at the bottom here to watch it yourself. Okay, so we've shown so far how we can recover known objects through shift stacking, but what about unknown objects? Well, we can apply the same idea, but instead of just shift stacking along one path, we now stack the frames along all possible orbits of interest to search for a systematic increase in flux, indicating the presence of an object moving along a path. We visualize the results of this search in an information-dense aggregate image that we call a best ever frame, where we record in each pixel the highest summed flux attained over all possible shift stacks. If nothing exists along a given path, the fluxes add up to a very small value since we're just adding up deviations from the baseline flux of that pixel. But if something is there, then it will be captured in our resulting image. We demonstrate this process with 3 distant objects at different magnitudes, with the results shown here. In the leftmost column, you'll see the recovery of each object by shift stacking directly along its known orbital path. The second and third columns, however, include no input orbital information about the objects. We just look for any object in the vicinity of where we know these objects exist. Between 40 and 800 AU, we should be able to capture anything that is bright enough for our detection limits. And we recover 2 of the 3 objects. And the dimmest one here, TG422, is not recovered in our blind search, which provides a sense for our limiting magnitude. And while I'm here, I'd like to quickly point out that while these objects aren't quite planet-sized, they're not exactly small either. So Sedna and BP 519 are both larger than Saturn's moon Enceladus, which has a radius of 252 kilometers. The pipeline used in our search includes an automated local maximum finder, injection recovery test to determine what types of objects we can expect to reliably recover, and false positive vetting with 2 independent data reduction methods. Our first paper summarizes all these methods and applies the algorithm to search for new objects around the galactic plane, with the motivation that this has historically been a very difficult region of the sky to search for dim point sources due to the high stellar density and thus confusion of signals. We did find a set of candidate objects that passed our vetting tests and that we're now working on following up. And of course, the journey does not end here. We're now working on refining our techniques to push these detection limits towards dimmer and more distant objects. We're also further automating the candidate detection methods by incorporating convolutional neural networks, with the ultimate goal of carrying out an all-sky survey in the distant solar system with the TESS dataset. Beyond the Planet 9 use case, the same survey method can also be used to study any other high inclination solar system populations as well. An exciting example application is illustrated here. Many of you may have heard of the 2 interstellar interlopers, Oumuamua and Borisov, that were recently discovered. And both of these objects came from the direction of the solar apex, which is the direction that the sun travels in the galaxy relative to the local standard of rest. This is well within the TESS field of view, and in particularly is fairly well aligned with the TESS continuous viewing zone that overlaps across all sectors, providing around 350 days of continuous viewing. TESS may be well suited to either place number density limits on these interstellar objects, or if we're very lucky, maybe to actually find a couple of them. And thank you for your time. Feel free to contact me if you'd like a copy of the paper, and it will also be available on archive this evening.
Can people hear me?
Yes, Bonnie, you're good to go.
Okay. Hi, I'm Bonnie Verratti, and I'm from the Jet Propulsion Laboratory. And I'm going to talk about Pluto and Glory. So we're changing scale here a little bit. We're going from these dim Kuiper belt objects to the brightest Kuiper belt object, something that is way more than not a planet. Okay, so we're all familiar with the opposition surge. If you look at the moon as it enters its fully illuminated face, the full moon, it gets bright, much brighter than you would expect from lower phase angles. Okay, I'm going to explain what a phase angle is in a minute. Well, we've looked at Pluto and have found that it does exactly the same thing. When Pluto is fully illuminated, it gets much brighter than you would expect, just like the Earth's moon. So let me first of all explain, this is in one of my few technical slides, what causes the opposition surge. So the solar phase angle is the angle between the sun, the target, and the observer. So let's look at the observer here above a planetary surface. It could be the moon, it could be the Earth. In this case, we're looking at Pluto. So if you look at the sun, if it's not behind you, if you're not looking at a directly illuminated surface, the particles that make up the surface, sometimes we call this irregular, cast shadows. And as the sun, the angle of the sun is high in the sky, it changes to a configuration where it's right behind us. Those shadows very rapidly disappear. So that's viewpoint number 2. If we go from viewpoint number 1, where the sun is over to the side, to where the sun is directly in back of us and the object is fully illuminated, those shadows cast by particles in the surface of the body, those shadows all rapidly disappear. So this is what causes the opposition surge. There are other effects. Bruce Hapke has a model that applies to multiply scattered photons. If these photons travel equal paths within the particles and are focused back at the observer, that causes an additional surge. So here's the thing. Most of what we've learned about Pluto has come from New Horizons. This was a spacecraft that encountered Pluto in 2015, and it revealed a body that is geologically active. It has glaciers, active glaciers. The only activity of that sort outside of the Earth. It has transport of volatiles, of frosts. There's possibly snow on the dwarf planet, though that idea has been criticized. But there's one thing we never saw from the spacecraft. We never saw Pluto fully illuminated. We were not able to see Pluto at opposition. So to do this, we have to depend on ground-based observing. So we did some observing of Pluto during a unique event that occurred in 2018 and 2019, and it will not occur for another 161 years. This is when Pluto is fully illuminated. This doesn't happen very often because Pluto's orbit is inclined. So in order for it to be fully illuminated, the sun and the Earth and Pluto have to be aligned. And this only happens when the plane of Pluto's orbit crosses the plane of the sun and the Earth, and Pluto and the Earth are in the intersection of those planes. So that's not going to happen for another 161 years. So we used the Caltech adaptive optics system. The reason you have to use adaptive optics, now this is a system on a telescope which corrects for the turbulence in the Earth's atmosphere. The reason you need to use this system is that Pluto and Charon cannot be resolved otherwise. If you look at them in a normal telescope, they're just one object. So we use this adaptive optics system. And there on the right, you see the Pluto and Charon as seen through the adaptive optics system at Palomar Mountain using the 200-inch telescope, the Hale telescope with adaptive optics. Now, if you look at the images that we saw from New Horizons, that's on the left. Of course, we see highly resolved objects. You can see the active glaciers, the dark regions, the mountains, the polar caps. And on Charon, you can see the red polar cap, the melted hemisphere. You can see all that stuff, but you only see that in an instant in time. If you look from ground-based observations, you can map and understand Pluto through a long time period. So that's what we did. We observed it as it reached full illumination. We were able to integrate, look at the brightness of both Pluto and Charon as it reached this fully illuminated phase. So that's what I'm going to report on today. So here's the answer. Now, just for comparison, I show a couple of other objects. The moon, this is from the Clementine spacecraft. So what this graph shows is the increase in brightness as we go from a solar phase angle of just 2 degrees. This is almost full illumination up to full illumination, which is a phase angle of 0 degrees. So this graph shows the increase in brightness just at that last moment when the object becomes fully illuminated. So this is in astronomical magnitudes. So like 0.3 to 0 corresponds to about a 30% increase in brightness. 0.2 is about 20%, and 0.1 is 10%. So you can see the moon does increase about 20% in that final 2 degrees. And we're all familiar with that because the moon becomes very bright when it does reach full phase. Rhea, which is a icy moon of Saturn, this is from the Cassini spacecraft, has a little bit more. It's more like 30%. But if we look at Pluto, it really increases in spades. Let me show you what our data looks like. Each of these is one night from the adaptive optics system in the Palomar. So this is a huge increase. Now, we were scheduled to get data between 2 degrees and a half degree, but we got wiped out by COVID. The observatory did have to close in March, And we had 7 nights to observe these larger phase angles, but we've reapplied to have them in 2021. So we will hopefully get those data, but right now we don't have them. But just from the small amount of data we have in this geometry that is not going to be repeated for 161 years, you can see that it has a huge surge greater than the moon or any of these other icy satellites. So here are the conclusions: that Pluto exhibits a huge surge in brightness. It's about 30 to 35 degrees, 30 to 35% in the last half degree of solar phase angle. The small phase angles we observe, which are only about 0.01 degree, will not be visible for another 161 years. So we were very lucky to capture this unique geometric event, and we're thankful to the TAC for giving us the time. This opposition surge is greater than that of the moon and other bodies so far studied. And I'd also like to point out that this surge is greater than that seen on other Kuiper Belt objects. Dave Rabinowitz has a paper published, I think roughly about 10 years ago, where he did see some other Kuiper Belt objects at small phase angles, and they don't exhibit this type of surge. So we've concluded that this effect may be due to an unusual surface structure, perhaps caused by ongoing volatile transport or deposition of haze particles from Pluto's atmosphere. Pluto has a haze layer that we believe is composed of particles of organic molecules, complex molecules that rain onto the surface of Pluto. That this may be part of the reason for the surge. It may be also freshly deposited volatiles due to active geology or seasonal volatile transport. So I just wanted to point out 2 papers. One of them was by my colleague, John Hillier, as the first author. And this is a model of Pluto's atmosphere that includes these data. That's been accepted to Planetary Sciences Journal. And we just submitted a paper to APJ Letters that has this data, the data of the opposition surge. So I want to thank everybody for listening. Thank you.
Hi, my name is Rohini Giles, and I'm a research scientist at Southwest Research Institute in San Antonio, Texas. I'm talking today on behalf of the UVS instrument team on NASA's Juno mission to Jupiter, and I'm going to be discussing some unexpected observations we made, bright flashes in Jupiter's upper atmosphere that we think are strange phenomena known as transient luminous events. The work that I'm presenting was published today in JGR Planets, and a preprint is also available on the archive. I'm going to start by talking about normal lightning on Jupiter. We think most lightning on Jupiter is generated in a pretty similar way to Earth in the planet's deep water cloud layer. And we've observed this lightning with a range of different spacecraft, starting with Voyager 1 back in the 1970s, which detected small bright flashes with its optical camera. The most recent mission to observe lightning on Jupiter is the Juno mission, which has been in orbit around Jupiter since 2016. Juno has actually observed lightning using 3 different instruments: the microwave radiometer, the WAVES instrument, and the Stellar Reference Unit. The most recent observations by the Stellar Reference Unit actually had a surprise result, showing that some of the lightning is located a little bit higher up than we previously thought, but it is still relatively deep in the atmosphere, below the planet's ammonia cloud tops. And then we come to another Juno instrument, the ultraviolet spectrograph, or UVS for short. The main goal of UVS is to study Jupiter's spectacular auroras, which are really bright in the ultraviolet. Juno is a spinning spacecraft, and as the spacecraft rotates every 30 seconds, the UVS instrument observes a swath of the planet. This allows us to build up ultraviolet images of the aurora. And in the process of putting together those images, we noticed that very occasionally we saw these surprising, short-lived, bright flashes. You can see an example of that here in the image on the left. So the main part of the image shows the bright aurora around Jupiter's southern pole, but up in the top left, highlighted by a solid yellow circle, is a tiny bright flash. That flash was incredibly short-lived, just a couple of milliseconds long, and was really unexpected in our data. We then went and searched through all of the data that we've taken over 4 years of the mission, and we found a total of 11 flashes, all with very similar properties, and those are all shown here on the right. Given all the other Juno observations of lightning, that might be the first thing that comes to mind, but in this case, we know that it can't be lightning. Jupiter's atmosphere is incredibly opaque in the ultraviolet, which means that we can't see down to the cloudy regions of the planet where lightning is generated. So instead, we're looking at something that looks a little bit like lightning, but is much, much higher up in the atmosphere. And what we think that we're looking at might be transient luminous events. This is an atmospheric electricity phenomenon that is seen on Earth, but hasn't previously been seen on other planets. TLEs are bright flashes of light that occur high up in the Earth's atmosphere and are triggered by a lightning strike in an underlying thunderstorm. There are several different types of TLEs that have been observed in the Earth's atmosphere. Sprite are these jellyfish-like features with long red tendrils extending downwards. And they're triggered when a lightning strike down at the cloud layer generates a quasi-electrostatic field at very high altitudes, which in turn causes electrons to accelerate and collide with nitrogen molecules, producing red emission. Elves have a somewhat similar mechanism, but in their case, the lightning strike down below generates an upward moving electromagnetic pulse, which then causes diffuse ring-shaped emission. In both of these cases, the flashes of light are very short, no more than a couple of milliseconds long, and they're also very high up in the atmosphere, which means they're often hidden from view by the thick thunderstorms that are causing them. So overall, they're very difficult to see. In fact, some of the first people who reported seeing sprites in Earth's atmosphere were pilots in World War II, who reported seeing strange red flashes high up above the clouds. And it wasn't until 1989 that a sprite was actually recorded on a camera for the first time. These images here were taken from the International Space Station. And from orbit, it has a great view of things that are happening really high up in the atmosphere. The whitish light that you can see is normal lightning within a cloud. And then high up above that lightning is a red-colored sprite. Orbiting spacecraft are a great way of observing TLEs, and there's actually an Earth orbiting mission called Taranis, which will launch next month and will be focused on studying them. What I've spoken about so far is all on Earth, and so far TLEs have only been observed on Earth. But there have been several theoretical studies which have predicted that elves and sprites should be also present in the atmospheres of other planets that have lightning, like Jupiter, Saturn, and Uranus. These theoretical studies have made predictions for what elves and sprites should look like on other planets. And when we compare those predictions to our mysterious bright flashes, we find that there's a good agreement. Firstly, as with Earth, any TLEs on Jupiter should be extremely short-lived. And we find that our bright flashes decay exponentially with an average lifetime of just a couple of milliseconds. On Earth, the bright light is caused mostly by nitrogen emission. But on Jupiter, the atmosphere is mostly hydrogen, so we would expect the emission to be hydrogen dominated instead. And when we look at the spectra of our bright flashes, that is what we find. The prediction papers also calculated that they would expect Jovian TLEs to form about 250 to 300 kilometers above the 1 bar level. And for reference, lightning is forming below the 1 bar level, so this is a lot higher up in the atmosphere. And we find that our bright flashes are located at about 260 kilometers, so that is also consistent. And then the last prediction is that they should occur in conjunction with a lightning strike, since that's how they're generated. And that is one thing that we don't yet have direct evidence for. We do have indirect evidence. When we look at the regions where these bright flashes occur on the planet, they're mostly in regions of the planet that are known for having lightning. But we haven't yet seen an actual lightning strike at the same time as one of our bright flashes. Even though there are 3 other instruments that can see lightning on Jupiter, they all have slightly different fields of view to UVS, so catching sight of lightning at the same time is difficult. But as the Juno mission continues, we'll keep watching and hopefully we will get lucky. So in summary, we see short-lived bright flashes of ultraviolet light high up in Jupiter's atmosphere. And the properties of these bright flashes are consistent with transient luminous events known as elves or sprites. TLEs were only observed for the first time on Earth 40 years ago, and they've never previously been seen on another planet. So this provides an exciting opportunity to learn more about electrical activity in planetary atmospheres. As the Juno mission continues, we will keep taking observations and try to learn as much as we can. Thank you.
So, hello everyone. This is Noemi Pinilla-Alonso. I am from the Florida Space Institute at the University of Central Florida. And I'm here today to report a detection of an irregularity in the leaf of Manoetius South Pole, and also of the analysis of data that provide an improved orbital solution. So this work has been submitted to the Planetary Science Journal and will be available soon in the archive. And also there is a second paper by Popescu et al. That is in preparation. So in a nutshell, what you're going to see here are observations from 11 different telescopes. When we gather light curves, 13 light curves of what is called the mutual events of Patroclus and Manoetius. These observations were done in 2017 and 2019. So one kind of these light curves, the ones that correspond to superior events, are shallower and asymmetrical. And this needed to be explained, and we explain it as due to a void in the leaf of Manoetius. So as said before, our light curves also provide a refined orbit of the pair, and all of this has vital information that is key to optimize the observing sequence of the NASA Lucy mission when they fly by the Patroclus and Manoetius system in 2033. But also, as Patroclus and Manoetius are primitive bodies, they provide a lot of information about the birth of this ancient binary small body and of our own solar system. So let me first introduce you to the Jupiter Trojans. So the Jupiter Trojans are these green dots that you can see on the animation on the right, that are small bodies that have been trapped by Jupiter gravitational field, and they orbit, sharing the orbit with them around the sun. So they go into swarms, one ahead and one after Jupiter. At this moment, there are more than 7,000 cataloged, but it's thought to be 1 million of Jupiter Trojans in the solar system. As mentioned before, these are really primitive bodies that form in the very first stages of the formation of the solar system. So they are fossils that hold important information about those stages. But also, we don't know so much about the Trojans, and actually, even if they classically are understood as asteroids, we are not sure if they could also be comets or even Kuiper belt objects. In the period between 2025 and 2033, the NASA Lucy mission will fly by 6 of these targets. One of them has a tiny moon, and another one, that is the one that we are studying today, is a binary formed by 2 components that are Patroclus and Manoetius, and that I like to refer to as the odd couple. So this binary is formed by 2 different asteroids or Trojans that swirl one around the other every 40 days. They have very similar size, around 100 kilometers, and they are expected to be similar to ellipsoids. Every 12 years, when the plane of the orbit of these bodies align with the Earth and the Sun, they go through what we call a season of mutual events. So as you can see, there is in their movement, there is 1/2 of the body that is illuminated by the sun. So these bodies reflect the light that they receive from the sun. And when one passes in front of the other and interrupts or blocks the sunlight, they cause a shadow on the surface of the companion that you can see now, or you can see now, always in the one that is on the back, because the one that is on the front is blocking the light from the sun. So this is what we call mutual events. And they happen every 12 years, and they happen more or less during 1 year, every 4 days. So the last season, that was the last one before the launch of the NASA Lucy mission, happened in 2017 and 2018. And for that, we got ready and we applied for observing time at different ground-based telescopes. And we succeeded at 11 of them to perform observations during 1 year of different events. So you can see here on the right that these telescopes that participated in this study grow from Taiwan to Mexico or Arizona in the US, and they include the 10 meters GTC telescope in the Canary Islands that really provided a very detailed light curve. That is the one that gives us a very cool result. So what do I mean when I refer to a light curve? Or what kind of observations are the ones that we do? So what we do is we observe from ground-based telescopes. So as Bonnie referred before for Pluto, we see these two bodies as one only body. And we stare at them for some hours to collect the amount of light that we receive from them. This amount of light is almost constant during all the movement around, except when one passes in front of the other, that you can see here, when in this case, Manoetius is blocking Patroclus, there is less area exposed, and as the area is related to the light reflected, so it is related to the amount of light that we see. Here on the right, you can see at the zero, the continuum of light when they are not blocking each other, and as soon as they block, the light that we receive dims and decreases to reach a minimum, and then goes up again to the level of the continuum. So just to show you our data, this amazing collection of light curves corresponds to 13 mutual events. And you can see here on the second column, the first two light curves are partial light curves. There are others also in the collection. This means that we could not observe the whole event. The timing of these events, the moment when they start and when they end, depends on the orbit, on the determination of the orbit. So the predictions were not so accurate as we had wanted. And some of the events ended up after the sunrise. So we didn't collect the light curve completely. Also, there were sometimes weather issues or telescope issues. But if you look at the first column, the first two light curves are really what we would expect and what I showed before in the animation, where we have a continuum of light before they start occulting. Then there is the timing of the beginning of the event, when the light starts to decrease. There is a minimum, and symmetrically, as if we were looking this in a mirror, there is an increase again up to the same level of the continuum. These light curves correspond to the moment when Manoetius is occulting Patroclus and are called inferior events. But the light curve that caught our attention, that was collected at the Gran Telescopio de Canarias, is this one that I'm showing now on the right. On the diagram on the left, you can see which was the configuration of this event at the maximum, so the minimum of the light curve, and it corresponds to the north pole of Patroclus occulting the south pole of Manoetius. So the light curve that you can see, that is the blue points, does not resemble the yellow line that corresponds to the prediction and the model light curve. It is not only shallower, but also the timing of the beginning of the event is different, is shifted by at least 40 minutes. The timing of the minimum is shifted by approx 1 hour, and the light curve is asymmetrical. So this really told us that there was something happening with this system that was not only related with the determination of the orbit. And our analysis is going to tell us how to explain this light curve, and is what I'm going to walk you through this slide. The image on the left was the best image that had been collected from the system of Patroclus and Manoetius from a ground-based telescope by Marquis et al. In 2006, and was done with adaptive optics that allows you to resolve the two components. So you have there Patroclus and Manoetius, and what we were expecting, what you can see here, is that they resemble a perfect ellipsoid with maybe regular limbs, but the limbs are not so well defined in this image. So imagine that we would have a void or a crater on Manoetius, on the south pole of Manoetius. Then the area that would be occulted during the event would be smaller than expected. And so we would have more light coming from the surface than if we had been blocking the whole area. And this you can see here on the animation. The first one is going to be an inferior event, so a regular one and symmetrical one. And with the void on the south pole of Manoetius, when Patroclus passes and blocks its surface, this is the kind of light curve that we can see. That if you remember the previous slide, resembles very much the light curve that we collected in December 8th. So to wrap up, I'm reporting here the detection of a void on the south pole of Manoetius that is at least 100 kilometers deep. And I say at least, that is what you can see in the artistic representation and in the diagram below, because the event that we observed did only go as deep as 11 kilometers. So this curve that you can see here is traced point by point from our light curve. And we have more light curves that we are analyzing now and that go deeper. So they may even reflect that this void is larger than what we are detecting now. So which are the implications for this? First, is critical for the planning of the observations of the NASA flyby of this system. Second, this was the last time that we could observe these events before the next season that is going to happen in 2029. So for all the design before the launch of the observing strategy, this determination is key. But it has also physical implications that are related to our knowledge of the birth of this system and also of the birth of the solar system. So the Patroclus and Manoetius system is composed by primitive asteroids. So these asteroids are supposed to have formed in the first million years after the birth of the solar system. So everything that we get to know about their mass, their density, composition, and structure tell us about how the solar system was at these first stages of its formation. Also, this system is an ancient one. It's supposed to have formed in the first 100 million years after the formation of the solar system. So it's important to know how these bodies were before pairing one to the other, or if they have evolved to the situation that they are now. And these are the implications. So thank you very much and stay tuned. Pinilla-Alonso et al. Is a paper that has already been submitted and will be soon archived.
Okay, thank you to all the presenters for presenting. You may now turn on your videos. Anyone who has a question can click on the Q&A button at the bottom of Zoom and ask questions. You can also upvote other people's questions. And Rick, do we have questions?
We do indeed. So we have 3 questions queued up for the first one each for the first 3 speakers. These are all from Govert Schilling, a freelancer in the Netherlands who's currently writing for Sky and Telescope magazine. So let me switch myself to gallery view so I can see everybody. All right, so this is a question for Melina Rice from Govert. When do you expect to be able to put upper limits on the brightness and size of Planet 9 using this method? And what would those limits be?
So this is really a question of how fast I can work, because the data set already exists. TESS has already observed the entire sky, and we really just need to improve our tools to pull out the dimmest objects. And it is true that TESS is continuing to observe, so the longer we wait, the more data we have. TESS is currently in its extended mission, and it's observing everything a second time. But ultimately, our goal is to rule out objects down to about magnitude 22, and it seems about doable for objects outside the galactic plane right now, but in the galactic plane, it's a little bit tougher because we do have extra stellar confusion. So right now, kind of the limiting factor is just how much time it takes to implement a couple of updates to the pipeline, which involve improved pre-processing. Right now, we don't try to remove foreground asteroids at all, so those create systematics, incorporating these convolutional neural networks, and then also incorporating data from the TESS extended mission. I just started this project about a year ago, so if that gives a sense for how quickly you might expect it, hopefully within a year, but I can't really make promises because it just depends on how fast I can do things.
Okay, thanks very much. So the next question from Govert is for Bonnie Buratti. Does it matter which part of Pluto is facing us, for example, Sputnik, Planitia, or something else, during your observations?
Okay, that's a great question, and I probably should have gone over that in the talk. And it turns out, no, we were lucky to get the minimum phase angle on both hemispheres of Pluto. As you know, one hemisphere has this bright, the heart of Pluto, Tambao Regio, which has the active glaciers, active geology. And then the other side, which we didn't really image very well with New Horizons, we also were able to capture that in 2019. So both years we were able to get the lowest phase angles, which fortuitously are on opposite hemispheres of Pluto, and it looks like both sides have that huge surge. And we attribute that to possibly two things. The first thing is that if it is due to this haze, that these haze particles, that these aerosols that fall into the Earth, those are global on Pluto. And the other thing is if it's volatile transport, seasonal or otherwise, due to active geology, it would be on both sides. So yeah, we see it on both hemispheres.
Very much. All right, and the next question, again from Govert Schilling, is for Rohini Giles. I think you may have addressed this already, but let's ask it anyway. Is there any chance of seeing the UV flashes simultaneously with visible lightning flashes, maybe by pointing the different Juno instruments in exactly the same direction? Oh, you're muted at the moment.
Yeah, so unfortunately, we're probably not going to be able to see simultaneous flashes between the visible light images that the Stellar Reference Unit makes and our UVS instrument. That's because the Juno spacecraft has kind of three sides, and instruments can be on any one of those three sides, and we're on a different side to the Stellar Reference Unit. So as the spacecraft spins, we see things with a 10-second offset to them. So we would be able to see a flash that happened 10 seconds before us, but not at the same time as us. And that time gap is really too big to see simultaneous flashes. I guess if there was like a really big lightning storm where loads of flashes were going off, that might give us a hint, even if it was like over a slightly different time period. Our best bet for seeing simultaneous lightning and TLEs is actually from the WAVES instrument. So in that case, they observe waves that propagate along magnetic field lines. So we have to be very lucky because we need the magnetic footprint of the spacecraft to match our field of view, but that could happen in theory on occasion. So maybe we'll be lucky with that.
Okay, at the moment, I don't see any more questions. So if anybody in the audience has another question, please get it into the Q&A box pretty quickly. Otherwise, I think Shantanu is going to wrap this up.
I had a question for Bonnie. Do you see, or do you have a phase curve for Charon? Or are you planning to do the same work? You're in mute.
Myself here. Okay. Yes, we do. And it does show the same type of surge. It also has a huge surge. Our signal wasn't quite as good for Charon, but it also shows a somewhat broader surge, but the amplitude is as large. And, you know, we can't quite figure that out. One of the ideas we have in this paper that we just submitted, that I'm going to put on the archive as soon as I get a chance, was, you know, there's this idea by Will Grundy that the red polar cap is actually accreted. There's methane from the atmosphere of Pluto, and this may include aerosols, that are accreted onto Charon and gives it an unusual color and possibly surface texture. So it could be also due to that factor, that there's also some, although there's not currently active geology on Charon, there could be some type of surface process that is unique to the system. So yeah, we see that.
I have another one for Noemi. Are Are there any other possible causes like phase angle effects for the unusual light curve, or the crater is the only explanation?
Of course, it's not the only explanation. I think there are other effects that are adding up. So, and for instance, the models that we run for the analysis of the first light curves are very simple. So they use circular bodies. For the extended analysis that we are doing now, we have seen that that is not useful at all, that we really have to resemble ellipsoids. Also, shadows on the limb are affecting for sure. Maybe there is some kind of albedo variation due to composition. So there are other things that would be affecting, but such a big difference in the light curve, it would be very difficult to explain it with these other factors. So when we analyze the standard sample with more light curves of superior events, we will see how all of this develops.
Okay. So I see there are no more questions. Oh, there's one more.
Okay. Yeah, this one just came in from Renu Malhotra for Bonnie. Perhaps a naive question. Does Earth have an opposition surge? If so, how large is it? I understand let me finish it. I understand the geometry is challenging, but perhaps it's been observed from the moon or from other spacecraft.
That's a good question. And there are a couple issues there. First of all, and I don't know the answer to it. I have looked for it, wasn't able to find it. There's a couple things about Earth. First of all, it has an atmosphere. And even though Pluto has an atmosphere, when you look at it fully illuminated, you don't see much of the atmosphere. You see it mainly at high phase angles and forward scattered radiation. So I think the Earth's atmosphere would mute the opposition surge somewhat. And I honestly do not know of any observations, at least that have been published, that show quantitatively an opposition surge on the Earth. It's a mystery. I don't know. It's a good question.
I think that's it for the questions.
Okay. In that case, thank you, everyone. Those were a very interesting set of presentations. Join us tomorrow again at the same time, 11 a.m. Pacific, Eastern, 8 a.m. Pacific, for another set of 4 interesting talks. And you can find the YouTube video on the AAS Press channel of today's briefing, as well as the presentations and any press releases on the meeting website by going to press information. Thank you, everyone, for joining us. See you tomorrow.
Bye, all. Thanks very much.
Thank